Hello everyone, and welcome back to the series on linear algebra. Today we're going to be taking another look at matrix decompositions and take a look at what is known as LU decompositions. So let's quickly give a quick run through of what we discussed last time. So suppose that you have a square matrix, A n by n, with n independent eigenvectors, let's call them u1, u2, and um, with associated eigenvalues lambda 1, lambda 2 down to lambda m. If these things do exist, in particular independent eigenvectors u1 through um, then we can express A as a product of three matrices. U, the matrix containing the eigenvectors, U inverse, its inverse, and obviously that inverse exists if these eigenvectors are all independent of each other, and D, a matrix containing the eigenvalues on its diagonal entry. Right? So this is going to be what we refer to as an eigenvalue decomposition. Right? So this is our eigenvalue decomposition. And obviously this exists if and only if A is what we call diagonalizable. Diagonalizable, right? So not every matrix is diagonalizable, right? So this is one of these downsides of eigenvalue decompositions. Okay, and obviously if this matrix does have this expression, right, so does diagonalizable mean invertible, for example? Well, if it is invertible, then A inverse would be equal to just the inverse of u du inverse, and then that would be equal to what? So the inverse of u would just be u, and then we have the inverse of d, and then we have u inverse over here, right, because it applies in reversal fashion. Okay, so does this necessarily exist? Obviously not, because it's possible that you have independent eigenvectors, but one of those eigenvalues is equal to 0, right? Because keep in mind, what is D inverse? Well, D inverse is just going to be the reciprocal of the associated eigenvalues on the diagonals of that matrix, right? So if lambda is equal to 0, then 1 over 0 obviously doesn't exist. So diagonalizable does not necessarily imply invertible, and invertible does not necessarily mean diagonalizable. Okay? So obviously it has these downsides, but does this eigenvalue decomposition have any other downsides that we didn't mention before? Well, obviously, in order to find the eigenvalue decomposition, you need to find 1, the eigenvalues, and 2, the associated eigenvectors, right? So how do you find eigenvalues? Well, first you have to find the characteristic polynomial of that particular matrix, which requires the determinant of an m by n matrix, and then you need to factor that nth degree polynomial to find its nth roots. So overall, we can clearly see, and you can just do a 4 by 4 matrix as an example, that finding eigenvalues and also eigenvectors are very, very expensive. Right? They're very, very expensive, right? In terms of time and computation, right? So are there other decompositions that either A, have a little bit of an upside to them compared to eigenvalue decompositions? So let's formally state our question. So are there other decompositions of a matrix n by m that are less computationally expensive? Obviously the answer is yes, else I wouldn't be stating this question here. But today we're going to be looking at one of them known as an LU decomposition. So let's get right into it. So what exactly is an LU decomposition? Let's take, for example, the matrix A is equal to 4, 3, 6, 3. Now, I just want to give you the heads up, not every square matrix has an LU decomposition either, just like not every matrix has an eigenvalue decomposition. So does this particular matrix have an LU decomposition? If it does, then our goal is to find a matrix L and a matrix U, hence the name LU decomposition, such that this matrix L is a lower triangular matrix and U is an upper triangular matrix. Right? So we can view LU decomposition as just a factorization of A into two triangular matrices. And most of the time people will also require that the diagonals of entries of L, so the diagonal entries of L, is always equal to 1, right? So 1 all along the diagonal entries of L. Okay, so what is that going to look like? So we're going to be letting L be equal to the matrix 1, 0, and let's call this L2, 1, and 1. Right, so there we have our 1s on the diagonal, and this is clearly a lower triangular matrix. And we're also going to be letting U be equal to an upper triangular matrix, so U1, 1, U1, 2, 0, and U2, 2. Right? So this is going to be our upper triangular matrix. Right? So that's what we have here. So if we multiply L and U together, then what are we going to get? So we're going to have that L times U, which is going to be eventually A, is going to be equal to what? So we have 1, 0, L2, 1, and 1, multiplied by U1, 1, U1, 2, U0, and U2, 2. Right? And now let us perform matrix multiplication on these 2 by 2 matrices and see what we get. So what are we going to have? So we have LU is going to be equal to what? So we're going to have 1, 0 times U1, 1 times 0. So the dot product of those two vectors is just going to give us U1, 1 as our first entry. And if we do 1, 0 dot product with U1, 2 times U2, 2, so U2, 2 times 0 is just going to be equal to 0. So we're just going to be left with U1, 2. So we're just going to be left with U1, 2 in that particular entry. And then we can do similar for the second row of this matrix. So we're going to be doing this multiplied by that. So that's going to be equal to what? So that's going to be equal to L2, 1 times U1, 1. And then we're going to have 1 times 0. That's just going to be equal to 0. Right? And then our last value is going to be that row times that column. And that's going to be equal to what? We have no zeros, so nothing necessarily cancels here. So that's going to give us L2, 1 times U1, 2 plus U2, 2. Right? So that gives us that. Okay? So this we want to be equal to A, which as we see is going to be equal to 4, 3, 6, and 3 for our particular example. Right? But this is the general representation for LU, our 2 by 2 LU. Okay, so what are we going to be looking for? So we're going to be looking for 4 unknowns. We're going to be looking for L2, 1, U1, 1, U1, 2, and U2, 2. Once we find these 4 numbers, then we have our LU decomposition. So the very first thing we should be able to easily observe from this is that the first row of L times U equals the first row of A. Right? So the first row of LU is equal to the first row of A. That's by observation. And more importantly, it's U1, 1 in the first cell and U1, 2 in the second cell. So more importantly, this is the first row of U. Right? And U, remember, has 2 unknowns. It has U1, 1 and U1, 2 in it. So that means we immediately get 2 out of the 4 unknowns that we have. Right? So from this we can clearly see that U1, 1 will be equal to 4 and U1, 2 will be equal to 3. All right, so we're 50% done. Now let us work on the lower row of this particular expression and see if we can find what L2, 1, LU1, 1, and the others are equal to as well. So from the bottom left-hand corner, what do we have? So we're going to have that L2, 1 times U1, 1 will be equal to 6. So here we have that U1, 1 is equal to 4, so we can substitute that here, and then we can solve for L2, 1. So we clearly see that L2, 1 will be equal to 6 divided by U1, 1. So that would be the general expression for it. And we clearly see that if u11 is equal to 0, then this expression is not going to be defined. Right? So here we can start to see that, not all matrices have LU decompositions. And keep in mind, what is U11? U11 is the corner entry of A. Right? So if that corner entry was equal to 0, that would be U11, and hence L21 does not exist. Okay? So using our particular number, what do we got? So we have 6 divided by U11, that's going to be equal to 4. So we have that this is just going to be equal to 3/2. So that's going to be equal to our L21 value. And then, what do we have? So our last value that we seek is going to be equal to the last value, which is going to be U22, right? So the bottom corner of U. And we can get that from this last equation that we have here. So let's just sort of write that out. So we're going to have that L21 times U12 plus U22 must be equal to our value of 3 in the bottom right-hand corner of our A matrix, right? So this is going to be our general expression for that. And our goal is to solve for this particular expression. So we can easily just subtract both sides by L21 times U12 to get U22, and then we're done. So we're not dividing by anything here as long as U11 is defined, and life is wonderful. So what do we get? So if we substitute our particular values, we're going to have, let's see, so L21 is equal to 3/2, so we can write this as U22 is equal to 3 minus 3/2 times U12, which is going to be equal to 3 over 1. So that's going to be equal to 3 minus 9/2, and that's going to be equal to what? So that's going to be 6 minus 9/2, and that's going to be equal to minus 3/2. So that's going to be our U22 value. Great. So now we're done. So now we have our matrix A, which is equal to 4, 3, 6, 3, is now being factored into our LUs. So we have 1, 0, and 1. That's always going to be true for a 2 by 2 L. And we have that L21 is equal to, and we came out with 3/2, right? So this is our L matrix, and then that's going to be multiplied by our U matrix, and we found that the first row of U is the first row of A, so that's going to be equal to 4, 3 always. 0 is always going to be in that bottom left-hand corner for a 2 by 2 U, and we found minus 3/2 for that particular value in the bottom right-hand corner. Right? So this is the conjectured decomposition of A in terms of a lower and upper triangular matrix, and you should be able to verify that the product of that, and that is indeed our matrix A. Therefore, you have successfully performed an LU decomposition on this 2 by 2 matrix. So now that we've worked with how to find the LU decomposition, especially for a 2 by 2 matrix, now I want to introduce one of the very useful technicality problems of finding determinants via LU decomposition. Right, so if we take this particular matrix, that's a 2 by 2, and we've just proven that this is indeed the LU decomposition, how would we find the determinant via its factorization into L and U? So let's just work out a little theoretical statement. In particular, let us note that L is a matrix, a diagonal matrix, with diagonals all equal to 1. And remember that the determinant of a triangular matrix is the product of its diagonal entries. So if that is the case, via that little theorem that we've proved before, the determinant of a lower triangular matrix with unit diagonals will always be equal to 1. So using that piece of information, let's assume that we want to find the determinant of our matrix A, and let's assume that A has an LU decomposition, so we can write A as L times U. It doesn't always exist, but let's pretend that it does. And remember, the determinant of the product is equal to the product of the associated determinants, so the determinant of L times the determinant of u, but the determinant of L is just equal to 1 always, even for 3 by 3 or 4 by 4 or 10 by 10. So this is just equal to the determinant of u. So if you can find this upper triangular matrix, then you can easily find the determinant of A. Moreover, the determinant of u is again a upper triangular matrix, moreover a triangular matrix, so that means the determinant of A is just equal to the product from k is equal to 1 to n of that kth diagonal entry of matrix U, because it is indeed diagonal matrix or triangular matrix, right? So we have this particular property. Now, with respect to eigenvalue decompositions, we also had a very beautiful way of finding eigenvalues or determinants, because recall, if you can find the eigenvalue decomposition, which again is extremely expensive, the determinant of A is equal to the product from k is equal to 1 to n of the associated eigenvalues. Now, even if the function or the matrix does not have an eigenvalue decomposition, as long as it's square, it does have n eigenvalues, right? So you can just multiply them out and you can get the determinant. So let's actually use this exercise to sort of verify that this is indeed the case. So we have our matrix, which was 4, 3, 6, 3. And if we use our little clever trick, then this is just going to be equal to 4 times 3, which is going to be 12, minus 6 times 3, which is going to be 18. And we clearly see that's going to be equal to minus 6. So let's see if that actually works for our LU decomposition. So this is going to be the determinant of 1, 0, 3 halves, and 0 multiplied by the determinant of the matrix, and what was it? 4, 3, 0, and minus 3 halves, right? So we have these two particular matrices, and where is that? That's supposed to be equal to 1. So this is going to be equal to what? So this is going to be equal to 1 times 1. That's going to be 1 always, because it's a lower triangular matrix. But over here, what do we have? Well, that's just going to be equal to 4 times minus 3 halves, because it's just a triangular matrix. And what do we have here? So 4 times 3 is 12, and 12 divided by 2 is 6. We have a negative sign, so it's equal to minus 6, which is obviously the same exact thing as before. So it definitely does work out. Now, let's increase the number of rows and number of columns by 1, and let's assume that we have the matrix A, which is 3, 6, 9, 2, 5, 2, and 1, 2, 3. So it's actually a nice, well-behaved 3 by 3 matrix. I leave to you as an exercise to prove out a couple logistics for 3 by 3 matrices, but one should be able to show that the lower triangular matrix for this is going to be equal to 1, 0, 0, 2 thirds, 1, 0, 1 third, 0, 1 for our L. And U will come out to, so take a guess of what that first row will be. It will come out to 3, 6, and 9, 0, 1, minus 4, and then 0, 0, and 0. Right? So it appears that U does not have full rank. It has a full row of zeros. Okay, so if this is true, then what is the determinant of A? So you probably know that the determinant of 3 by 3 and higher can be quite annoying. 3 by 3 is not super bad, but 4 by 4 can definitely be stressful. But what would the determinant of A be? Well, keep in mind the determinant of A will be equal to the determinant of U, provided that U does exist. And what do we have here? So the diagonal entries are 3, 1, and 0. So the determinant is just the product of those numbers. So it's going to be 3 times 1 times 0, which is just going to be equal to 0. Right? Oh, we have that 0 is the determinant of A, so what can we immediately get from that? So we clearly see that 0 is an eigenvalue of A. That's one of the properties that we have for eigenvalues. And moreover, if the determinant is equal to 0, that means A inverse does not exist. Right? So we have that 0 is an eigenvalue of A. So we have one eigenvalue, so we don't even have to do the determinant, find the characteristic polynomial and factor. We can clearly see that that is true. And also A inverse doesn't exist. That's an immediate corollary from determinants. So we clearly see that finding determinants with LU decompositions is very, very efficient and is extremely not as expensive compared to that of, expansion by submatrices and stuff like that. But is there any other things that are a little bit more easier under the realm of LU decompositions? And one of the more important applications for LU decompositions is solving equations. So solving matrix equations, right? So how do we usually solve systems of linear equations via matrices? So this typically requires Gauss-Jordan elimination. Right? So what does Gauss-Jordan elimination do? Well, usually it takes Ax is equal to b and transforms it into a different system. In particular, let's say ux is equal to b prime, and then it uses back substitution, or it converts that upper triangular matrix into a diagonal and then divides by the diagonal entries. But for LU decomposition, again, let's assume that A has an LU decomposition, then we can write this instead as LU times x is equal to b. And we can rearrange via associativity of matrices and write this instead as LUX is equal to b. And then we can redefine ux as y, and then we're going to have ly is equal to b instead. Right? So Ly is equal to b is what type of system? Well, that's a triangular system which we can solve via back substitution. Right? But the first thing that we need to figure out is how do you solve this particular thing? Well, ux equals y is also a triangular system, but we don't know why. So how is this going to work? So step 1, we need to solve Ly is equal to b. Solve Ly is equal to b, and then, and obviously we're solving for y in that case, and once we solve for y, then how are we going to get x? Well, keep in mind y is just u times x, so then we can solve ux is equal to y, and we can solve that for x. And we can solve both of these, solve via back substitution. Right? Solve via back substitution. Okay? So we're going to be assuming that you can already calculate the LU decomposition and then proceed from there. So let's go back to our friendly little 2x2 matrix that we already proved the decomposition. So keep in mind, let's assume we have 4, 3, 6, 3. And let's create a matrix equation out of it, x1, x2. That's our end goal. And let's assume this is equal to 10 and 12. We can clearly see that 12 minus 18 is non-zero, so there does exist a unique solution for this. So the first thing we're going to do is we're going to perform an LU decomposition on this particular matrix A, which we've already proven to be 1, 0, 3 halves, and 1 times 4, 3, 0, negative 3 halves times x1, x2, and that's going to be equal to 10, 12. So what do we have here? So this is our L, this is our U, this is our X, and this is our B. So the first thing that we need to do is figure out what is Y. So what is Y? Y is going to be U times X, right? So that is going to be what Y is going to be when we solve Ly is equal to B. But keep in mind, what exactly do we need to solve first? We need to solve Ly equals B first, because right now we have L, y is some unknown vector, and then b. So y is y, an unknown vector, because x is part of y, and x is unknown, so y is unknown too. So let us solve the first equation. So we're going to have solve Ly equals b, and that's going to be what? So we're going to have 1, 0, 3 halves, 1, times y1, y2 equals 10, 12, right? So this is L times y equals b. So our u times x is hanging out underneath this y1, y2. So how are we going to solve this? Back substitution should be our best friend. So if we multiply this out, or write this in expanded form, we're going to have y1 will be equal to 10, and 3/2 y1 plus y2 will be equal to 12. So immediately from triangular systems, we can get the first value quite easily, and then we can substitute that into this. So we're going to have 3 times 10 is 30, divided by 2 is 15. That's going to give us 15 plus y2 will be equal to 12. So that means y2 must be equal to minus 3. Right? So that means that y will be equal to 10 minus 3. So now we have our y. So once we solve Ly equals b, then we're going to solve ux equals y. So what was our u? Our u, remember, is just 4, 3, 0 minus 3/2 times x, x1, x2, and our y we just found is 10 and minus 3. So our goal is to solve this via back substitution, and then we are done. So if we write this in equation form, we have 4x1 plus 3x2 will be equal to 10. And on the last row, this is the easiest row, that's going to be minus 3/2 x2 will be equal to minus 3. Right, so all we need to do is just reciprocate that minus 3/2 on both sides, and that's going to give us what? So that's going to give us x2 will be equal to, that's going to be a positive, so 3 times 2/3, that's just going to be equal to a lonely little 2. So once we have our 2, keep in mind that's x2, then we're going to have what? So we're going to have 4x1 plus 3 times 2 will be equal to 10. 3 times 2 is 6. Subtract that from 10. That's going to give us 4. And then we're going to have 4x1 will be equal to 4, which means that x1 must be equal to 1. Right? So that gives us that particular value. So once we combine these terms, that means our solution for our original system is just going to be 1, 2, and you should be able to substitute that into your original systems of equations to verify that that is indeed the case. So you can clearly see that we don't have to really use Gauss-Jordan elimination to find this particular solution. We can just use back substitution 2 times, provided that we do have the LU decomposition. Now, I just want to send out a quick disclaimer that some people will use Gauss-Jordan elimination to find the LU decomposition. But if you do the matrix multiplication way that I did introduce in the very beginning for higher n by n systems, you should be able to algorithmically build, using mathematical induction, the general closed form for the individual elements of these matrices. So technically speaking, it's just a formulaic inductive structure way of calculating LU, and then you can find determinants in the very trivial way by doing the product of diagonal entries of U, and 2 iterations of back substitution for solving linear equations, provided that the solution even exists. So I hope you enjoyed this quick tutorial and introduction to LU decompositions, and I hope you join me in the next video of this linear algebra series. Take care.